Okay, welcome back to our next Unit 2 lecture video, and this time we're going to be talking about the macromolecule that we refer to as lipids. This will have the most detail out of any of the four that we discuss. Now, lipids are also known as fats and oils, is how you've probably most commonly heard of them before. There are other designations for them, but that's what we're going to focus on. So AKA, again, means also known as. You're going to find fats and oils in products such as you see down here. Any type of meat, either mammal or fish, cheese, butter, chocolate. We're going to have a lot of that in a couple days for Halloween. Nuts and seeds, avocados, you name it. So fats are everywhere. Can they be good for you? Yes. Can they be bad for you? Yes. It's all about moderation. This little cat up here does not know anything about moderation. So for jobs and functions, there's going to be quite a few of them. All right, for the first one, we're going to have, it is a major part of all cell membranes. So you should have learned this in our COLA. We'll learn about it next unit. But every cell's membrane is made up of fat. They are for long-term energy storage, as we discussed previously. Plants store their energy long-term in starch. We're going to use fat. And once we turn it over to fat, all right, you can see in this guy here, all right, you do not want to get rid of it. You got to make your body start to actually burn fat off by dieting and exercising. Insulation, not only to keep warm, but to protect your organs from any type of damage or trauma they may receive. If someone were to give you an uppercut in your kidneys, you don't want your kidneys to burst or have a some type of contusion. So there is some fat surrounding your kidneys that hopefully absorbs and protects the organ from any type of damage. And finally, it is also a key component in what we refer to as steroids and hormones. We've already discussed the importance of some hormones such as testosterone and estrogen in previous videos. Now for the elements present, we already know these. It's going to be your CHO. But there will be no ratio this time for lipids whatsoever. All right, you're not going to see a 1 to 2 to 1 ratio like you saw in carbs. All right, you can have any number of atoms between carbon, hydrogen, and oxygen this time around. And finally, for building blocks, for carbohydrates, we had monosaccharides. For nucleic acids, we had nucleotides. Now, for lipids, we're going to actually have two building blocks. We're going to have what you call fatty acids and glycerol. All right, so again, fatty acids and glycerol. Make sure you pause this video at any time to help you get down all the notes before I proceed on. So what we're going to look at is lipids can be found in one of several categories. Our focus is mainly going to be on what we call triglycerides. And if you look at it, it looks like a jellyfish, doesn't it? Got like a little head up here, and you get the little tails coming down. So you can see the building blocks I just mentioned for lipids right here. Glycerol is the head of the jellyfish. And then these tails that we call fatty acid tails, which are mainly carbon and hydrogen, are attached to them. There's another class of lipids called phospholipids. That's actually what is in your cell membranes. You replace one of the fatty acid tails with a phosphate group. Then you can also have what we call steroids. We'll talk about those in our next lecture video for lipids, where they are very specific. They have an appearance of several carbon rings attached with one fatty acid tail. And there's another class called waxes that, again, we don't need to talk about really at all. This is going to be our focus, is triglycerides. Now, when we look at a triglyceride, which is what the majority of fats that we consume are, they always have a glycerol head, but the tails can differ. You might have really long tails or short ones. You may have tails that have a slight kink in them, or ones that are significantly kinked in them. All right, depending on which ones you get, ultimately relates to the properties that that fat's going to have. Is it going to be a healthy or unhealthy fat for you? Or is it going to be a solid or liquid fat at room temperature? So all those determinations will be made then on what the tails are going to be. So that's what we're going to elaborate on in the next couple slides. Before we do that, a triglyceride or lipid, again, is going to be made by the same type of reaction that we have discussed for both carbs and nucleic acids. And that is going to be a dehydration synthesis reaction. But this time, to make one triglyceride over here, one jellyfish, all right, we're going to have to connect 3 fatty acid tails to the head, or the glycerol molecule. So to do that, I'm going to have to pull out 1, 2, 3 water molecules to create those bonds, rather than just 1 water molecule when we were connecting, say, 2 monosaccharides or 2 nucleotides together. So every triglyceride is going to cost you or pull out 3 water molecules. So let's get into the discussion about if a fatty acid tail is going to make a lipid either saturated or unsaturated. Let's focus on the saturated, which are going to be the ones that are unhealthy for you. All right, saturated fats are going to be solid at room temperature. The reason for this is you are going to find only single bonds between carbons, and I'll explain this more in the next slide. All right, if you bring your attention down here to this triglyceride, each of these 3 fatty acid tails, these are drawn in shorthand here, each little point would be a carbon. There are no double bonds between any of these fatty acid tails, so they can get really close to one another, which makes them denser, which is going to make them solid at room temperature. So some examples of these would be butter and lard. Everyone knows where butter comes from. It comes from milk, all right, no matter if it's cow milk, goat milk, you name it. Lard is pure saturated fat from animals. So a lot of people at home, you may cook bacon, and then some of you or your parents may then pour off that liquid fat, put it into a coffee mug, it solidifies. That is pure animal saturated fat. That's what people used to use back in the day as actual soap. All right. Today, most times we save it, and you can take a little spoonful of it, cook or bake with that. It provides a little bacon flavor, and is also it's free. You don't have to go out and buy it, but it is very bad for you. Since it's solid, if it gets into your arterial, your artery system, it can become solidified and build up and cause blockages over time. Now, unsaturated fats, they're going to be the opposite. They're going to be liquid at room temperature. And the reason why they're going to be liquid is at least one of these 3 fatty acid tails right now that I'm pointing to, all right, at least one of them is going to have at least 1 or more double bonds between carbons. So if I were to point to here, let's say I put a double bond right here where my laser pointer is. All right, what's going to happen is the rest of this chain may kind of bend upwards this way and kink out. When that happens, you're increasing the distance between the fatty acid tails, as well as you're going to see that you can increase the distance between another triglyceride, which makes the molecules less dense, so they're going to remain liquid at room temperature. So an example of that would be any cooking oil, and there's dozens and dozens of varieties that you can choose from. So vegetable oil is what you cook with, or bake with, most times. Olive oil is extremely healthy to cook with, but there's other ones that are even better, such as corn, sesame, and peanut oils. They're all healthier for you. Why are they healthier? Because they will have more double bonds between carbons. So let's see what I mean by that. So here would be an example of one fatty acid tail that's saturated. You do not see any double lines or double bonds between carbons, which means then you have the maximum or saturated amount of hydrogens that can exist around that chain. Again, a saturated fat or saturated triglyceride, all 3 of its fatty acid tails will look like this. Now, when you get to a liquid or unsaturated fat, at least one of the tails in that triglyceride will have at least 1 double bond between carbons. So you see what I mean here. So you lose a couple hydrogens, you don't see any down below. And also, you see how the molecule is now kinked? All right, maybe it kinks upwards or it kinks downwards in this instance. All right, that is going to make it end up being less dense and liquid. Polyunsaturated fats are even better for you. They're more healthy. Now you're going to have 2 or more double bonds on a fatty acid chain. Or perhaps you have at least, let's say, 2 of the 3 fatty acid tails have at least 1 double bond. That would make the whole molecule also polyunsaturated. We're never going to say diunsaturated. You either go straight from mono or you go straight to poly. That's it. So when these molecules get kinked, here's what happens. Notice here, this is a triglyceride in a 3D shape. See how the fatty acid tails are straight? Well, here's how it looks chemically speaking. See, each tail has nothing but single bonds between carbons, and all three of them are saturated, so this whole molecule here would be solid at room temperature. So if you look at this little shorthand diagram, you have two triglycerides. Each one is saturated, so all its fatty acid tails are straight. You see how these two molecules can get really close together? So they can become more densely compacted, so they're going to become solid at room temperature and be butter or lard. But if you start introducing double bonds into any of these fatty acid tails, this diagram actually has all three fatty acid tails have some type of kink. You can see 1, 2 kinks here. Here you have 1 kink. Here you have 2 that are really close together. It kind of kinks down and then kinks back up. So this would be an example of a polyunsaturated fat, or triglyceride, a polyunsaturated triglyceride. See how they can't get close together anymore? Those kinks kind of end up spacing all the tails in one molecule, as well as space out the distance between two separate ones. They're going to be less dense. It's kind of like if you remember water being solid at room temperature, or solid when they're ice. Their hydrogen bonds space them out. Well, now these molecules can't physically get close together because the kinks in the tails force them from really getting compact. They're going to remain liquid at room temperature. The thicker an oil is, the less double bonds there are in the fatty acid tails. So it would have what you call a higher viscosity. The thinner or more watery an oil is, the more double bonds it's going to have, so the more spaced out the molecules can be. That oil, the thinner an oil is, the healthier it's going to be for you, because it's not going to end up adding to blockages in your arteries within your body, in your heart, or especially your brain. So the way we can find some of these are, again, focusing on saturated fats here. They come mainly from any type of animal product that you're going to eat, dairy, even coconut oil. Years ago, they said coconut oil is really healthy to cook with. It's like a wax. You take a spoonful, put it in your frying pan, and you fry with it. Hey, it's healthy. It comes from coconuts. But it's loaded with saturated fats, which are actually really bad for you. These can clog your arteries since they're solid at room temperature. Saturated fats don't really melt in your bloodstream. Your body temperature is not that hot to melt them. So over time, they can build up and clog your arteries. We're going to skip trans for now because we're talking about that in the next lecture video. So the next two, monounsaturated and polyunsaturated, these would be liquid at room temperature. We said monounsaturated has, again, just one double bond, which will put one kink in. So at least one of the tails of a triglyceride looks like this. It'll make them liquid. So olive oil, canola oil, peanut oil, these are examples of monounsaturated fats. These will be the healthier ones for you. But if you start putting in multiple double bonds in one chain or all three, then we're talking oils that you get from soybean, corn, straight from fish, which is why fish is much better to eat than it is red meat. There's also other wacky oils out there. One, for example, is called rapeseed oil. It comes from a plant called rapeseed, and it is phenomenal, but it is very, very, very expensive. All these oils are much more watery as a result of the multiple double bonds. So they're not going to help to clog your arteries. In fact, what they do is they lubricate your arteries, which limits the amount of saturated fat that can build up and stick to your arteries. So it actually helps and reduces heart disease. And lastly, why does oil float on water? Or really, why does fat float on water? Well, if it's going to float, first off, obviously it's less dense than water itself. Butter will sink, but still not dissolve. But go back to what we know. Fats are going to be mainly nonpolar. We said in the last unit, nonpolar doesn't dissolve in water because they have no charges. So when you see oil floating on water, what you're actually seeing is this. Pretend that this is the glycerol head. Now, the glycerol head is polar. See how oxygen is here and hydrogen's on the other side? Oxygen will win that tug of war and be slightly positive, or negative, I'm sorry. So the glycerol head's polar, which it likes water, which we call hydrophilic. But the tails are mainly nonpolar because they're just carbon and hydrogen. They're going to be what we call hydrophobic, and they're going to stick up towards the outside like your feet sticking straight up. If you have any questions, please reach out and ask me immediately. Thank you.